My name is Mats Gidstrand. I'm head of the department Systems and Data Analysis at the Fraunhofer Chalmers Center in Gothenburg, Sweden. I'm going to talk about NLME modeling, which is a nonlinear mixed effects modeling of dynamical system application for Wolfram Mathematica. Yeah, the abstract is for those doing this afterwards. But what is nonlinear mixed effects modeling? It's a parameter estimation methodology, which is very useful when model parameters vary between individual subjects, and also the amount of data per subject or entity are quite sparse. Nonlinear here refers to that it's the statistical model is nonlinear in the parameters. Mixed effects means that we have fixed and so-called random effects, and effects here for historical reasons are the same as parameters. Fixed effects are those parameters that are common to all subjects or have common numerical values for all subjects. And random effects are those parameters that are assumed to vary between individuals according to some probability distribution. And looking into an example, we see to the lower left typical data. Here it's drug concentration profiles from different individuals after an oral administration of a drug. And they look quite similar, but some are much higher and other are declining faster and so on. So it's not just measurement noise that make these differ, but it's also other stuff. And looking at the schematic model, here, the dose is the same for all individuals. We have some kind of absorption rate, which is also assumed to be the same, a volume distribution the same, but here is a clearance parameter, essentially how fast the body clears out the drug. That is assumed to be an individual parameter that can vary between subjects. And for this synthetic data, we can see some of this variation. Looking in this particular case, modelers or pharmacometricians, for those of you who are not in that genre, postulate different kinds of model structures. And in this case, this is a quite common structure. It consists of two differential equations and the concentration readout, essentially. And we have a measurement model, so we measure the concentration from blood samples, but it's corrupted by noise. And in this case, it's noise proportional to the concentration. So we have a variance that varies when the concentration varies, essentially. And this kind of estimation problem to fit the model to data or estimate the parameters can be done in different ways, of course. Maybe the most naive one is the naive pool data method, where one essentially fit the model assuming that all data comes from the same individual. It's just a replication of a number of measurement curves, essentially. But then, of course, you get quite crude parameter estimates due to this individual variability. Then we have the naive average data method, where if you have samples at the same time points as for all individuals, as we have in this particular case, we can empirically compute the mean value and the standard deviation of the data. And then we can fit the model to this mean data using weighted least squares. So where we have a large spread between data points, we will down weight, so to say, that influence on the parameter estimates. If we have quite a lot of data per individual, maybe it's very natural then to estimate one model for each and every individual and get out a parameter set for each and every individual. And then we can compute parameter distributions empirically, of course. So that is called the standard two-stage method. But for ethical reasons and also budget reasons and others, these data sets per individual is often quite sparse, at least in many applications. And then you can somehow, so to say, borrow from information from increasing the number of individuals. And that is exactly what the nonlinear mixed effects modeling framework does. It's assumed population distribution for some of the parameters that are assumed to be distributed over the subject population. And then one formulates and solves the full maximum likelihood estimate of this parameter population problem. And this is a well-known technique, but we have been working both into improving fundamental algorithms there with quite some success, and there's also some uploaded publications on that on the talk page for the conference. But we also, doing that way, we also pack it quite a nice number of the standard commands to do nonlinear mixed effects modeling in Mathematica, which I will demonstrate this talk here. Okay, so let's have a look at this rather small system, example system. We describe, and I will start by going through essentially generating the synthetic data for this, just to show where the variability comes from, so that there's no magic behind the scenes, so to say. But we define the system very much in a standard way according to Mathematica syntax. So we have the two differential equations and the concentration readout, and typical parameterized solutions of course can be computed by parametric and dissolve value in this case. And looking at the particular curve for some set of parameters, we see that we get something quite smooth and nice in this way. But now we would like to introduce this variability over the population. And the only thing that differs from this system description from the one above is essentially this term here. We have a parameter called eta1, the exponential of that. So this clearance, total clearance here becomes log normally distributed essentially, but it's quite common that one works with multivariate normal distributed random effects here. So if we specify that solution and in the same way look at the curves for this, here we now take 20 individuals that we sample for etas, and then we compute the response for those. And so this is the underlying model structure, and we have this population of individuals simulated. But now we would like to sample those at particular time points, and then also say that we have some measurement noise here. So this is the design of the experiment, which it's called when you sample things. And yeah, essentially we just generate the data by adding this measurement noise, and we can look at typical outputs of that. So this is typically how maybe the real data is generated. In this case, it was synthetic data, but very often one starts with images or pictures like this when we have measurements from clinical studies, or if it's yeah, from preclinical, it's in a similar way. Okay, but if one is using the NLMEModeling application, we start loading the package as usual. This is just a repetition of the same system that we have studied above. If we now are going to say that we have some spread over a population, we can specify, in this case, it's a very small variability, it's only one random effect. So it's this omega, and then we have a measurement noise covariance matrix to specify. And then we do define the design, the sample time points, and also say that, okay, we have a data structure that we eventually will fill with data. So when we do this, we get out something here that this is typically what right now is one subject. It has only the time points and then some covariates or something that are also tied to the subject. It could be inputs like those in this case. And we see that each and every individual have the same time points, but this is not a restriction. They can be specified in an arbitrary manner. But once we have that, this goes into a synthetic data generating function, where we also specify the system and the observation equations. We specify the the fixed effects parameters, those that are similar for all subjects, and we have to declare the eta1 or the single random effect in this particular case. And then this function essentially do exactly what we did above. So it's no particular fancy stuff, just to generate the synthetic data. And once we have data on that form, there's built-in visualization functions that can generate plots for the single individuals. And then once we have that, you can also do some nice formatting of these outputs and make some headings or axis labels and so on and so forth to generate and have a look at the data. Okay, but that is when we have the data. The real workhorse and the numerics number crunching in this package is this function, the nonlinear mixed effects dynamical model fit function. So the syntax is rather similar to when we generated the synthetic data. We have the first argument is the data, the individual time series from, in this case, 20 individuals. We have the model structure, the differential equation and observation equations. We have initial guesses of the parameter estimates for the fixed effects parameters. And then we declare our normally distributed random effect in this case, and we say that the measurement noise model is proportional. That was we can also specify it with equations, but there are some so to say pre-labeled things that are quite common here. So if we start this now, it's during it's going to parallel mode. I have a quite low-end laptop with only 2 kernels. But still it goes into parallel mode, and then it spits out while it's estimating some intermediate results, so that you can see that something happens and in what iteration you are. So every 10th iteration it updates where it is with likelihood values and gradients and stuff like that. And this will go on for about 1 minute. So I think this is the only live estimation I will do. The other ones will be loaded into the system, but I think it's nice at least to have it seen working at least for one time here. I can also say the computational effort behind this is quite large. It's quite big likelihoods functions where we compute gradients also by solving sensitivity differential equations to have quite robust stuff. Yeah, here we see sometimes when the solver get into some instability regions, it can actually even close the kernels. But in parallel mode, this is recovered and it continues to do iterations here. So it's soon finished here. And first, the point estimate of the parameters are computed, and when that is finished, it goes into a covariance or precision estimation mode. So you also get the precision value for the parameters eventually. Yeah, their estimation is ready, and now the covariance step starts, so that you get the standard error or relative standard error with the results here. And hopefully it will be finished. Yeah, covariance step succeeded. And now when it got ready here, you see these intermediate values, except the error messages here that we can just delete, went away. And the result is a fitted NLME model object. So we have tried to replicate the syntax or machine in Mathematica for other, like fitted linear model and so on and so forth. So this contains all the results, including the data. So it's a quite rich object as such. And it can be exported, of course. And if it's exported, it can be reloaded. So, but regardless now, if I execute this command, I will just load what was just computed. But I do that and just to make things, to show that it is there. And this model fit, this object now is stored in the variable model fit, and that could be prompted for different properties. And here's a list of the current properties. So as you see, these fitted model objects also built into the system. We have tried to enrich this also for the nonlinear mixed effects models. And one of the most, for presentation purposes, is the model summary table. So here you can have quite a large informative table on this particular run. So you can read off a number of metrics for the log likelihood and information criteria and stuff like that. But maybe the most interesting, or where you look first, is about the estimates here. And the values generated in the synthetic data was 1, 10, and 50. And we see here we are quite close for this estimate here. Of course, the noise makes it that we will never land on the exact values. And they are also have quite small relative standard precisions, a few percentage away from the values as such. And then we can have some visual feedback on this. We can have a look on top of the individual data. We can plot the population model fit, which is essentially the median model. Also, when it comes to the variability of parameters, of course, you can get per individual. You can get also what these individual curves or simulated curves should look like with the estimate parameters. Furthermore, there are like goodness of fit analysis plots, so that you can get an overview how good your predictions are versus observations. Here is the least spread ones. These are individual predictions versus observations. And if we only use the population prediction model, then of course you get a larger spread for the observations, but they are still quite close to the y=x line here. We also can have like weighted residuals with respect to time. There should be no trends or other things like that if error models and model structures are correct. And you can also do that versus individual predictions, essentially, where there also should be no actual patterns visible here. So this is quite nice when it comes to model evaluation things. And we also have something called visual predictive check, which is quite nice and well spread model evaluation tool in this area. And essentially what you do is that you say that, okay, we have the model fit object, it contains data and the model structure, but now you simulate 200 clinical studies of similar kind of that we have, that the data was for. And with these 200 in this case, you can say, okay, but let's look at these quantiles, the median, 10% and 90% quantile, and compute those with a confidence interval of 90%. And when we do that, that will take 30 seconds, so it's not too long, but let's have a look what it looks like. Then we get something like this. And so here we see all the dots are all the data. The smooth curve or gray curve here, that is actually the Monte Carlo simulated median. The black wiggly curve here, that is the data median, essentially. Then the gray zones around the middle gray curve here, that is these 90% confidence intervals. So what one would like to see here is that data is here, these 90% or these percentiles should be rather much on top of each other and or within the confidence band, essentially. So this is a popular tool in pharmacometrics to evaluate your models, and we have implemented that as well in our application package. All right. Next slide is also a number of Mathematica notebook pages. I will not go through that at all, but I will switch rather soon. But this notebook is possible to, it's posted on the conference page, the talk page of the conference. So you can go through that yourself. But a very similar one is the one on the third slide here. The only thing that differed was this gray arrow, if you didn't recognize the difference between these things. And in this case, it's actually a model where you use stochastic differential equations and not just ordinary differential equations. And this is something that is a bit up and coming in the pharmacometrics field, at least, and also in the single cell field, where we also are applying these methods. And so looking at the differential equation, this is a little bit larger system than before. It's only 3 differential equations, 2 ordinary and one stochastic differential equation. And it's stochastic because I say that, although the notation looks a bit as a regular one. But small w here, that's actually a white Gaussian noise process that if you integrate it, you get the Wiener process. And so this is actually have that kind of structure. And you have, in this case, we have 2 random effects, eta1 and eta2. One is still related to the clearance. The other one is related to E0, which is essentially the baseline of this response here. So it's when you have no drug or whatever, that should be pretty much a straight line that fluctuates a little bit since we have this stochasticity in the differential equation. But the mean value of that is essentially what is also, we also would like to fit, and that has some spread over the individuals. So let's have a look at that. I will not evaluate so much in this, but essentially everything looks very similar to what we have already seen in terms of how we define the system, how we generate the data, and the only thing that comes in addition is that we have to declare this W variable, and it's possible to have several of those as well, of course, and then there's a list of these variables. But in the same way as we declared the eta symbols, the random effects, we have to declare these white noise processes. And looking into some plots of this, we will not see that much difference if we put them very close to this one you haven't seen before, but you have seen this one. This looks quite similar to the ones on the previous slides, but it has, when it's injected into the response equations, you get some more variability due to this white noise process. And yeah, these are just replicates of the stochastic differential equations. And the interesting thing might be to see that, okay, here we have 2 measurement variables. So we have vector valued values measurements. When it comes to NLME dynamical model fit command, yeah, we have, for stochastic differential equations, we have to add these symbols that stands for the noise. And if you didn't see that, we had sigma here. We have, when it comes to the measurement noise processes here, we specify those by telling what measurement noise matrix, covariance matrix we have. In this case, we had some additive noise, and we have some proportional noise here for the concentration term, and for the response term there's only an additive covariance or additive error, so we get a constant, essentially constant covariance, and then that goes into the specification of the estimation command here. And yeah, by that, I think I continue over to left to have room for some questions also, to just briefly go through. There's a regular guide page for the application. And what we have seen is the main command is NLME Dynamical Model Fit, and it's object that is spit out with a number of different properties. We have a set of different model validation tools that makes life easier when it comes to debug or understand what terms you might have missed or should add in your differential equations. And you have a number of different both data generation and visualization functions. The math I skip. It's better to read the papers, I think, to really appreciate this. But very important, of course, this is teamwork at the Chalmers Center, both by people still at the center and those that are alumni and have left the Center for Industry, and that we collaborate very much together. And also some public funding that has supported this project throughout the years. There's a number of resources, both papers and some YouTube brief video of an introductory talk, and we also have a web page where the model code resides and so on. And by that, I end the presentation, and thank you very much for your attention, and leave the floor open to questions in the chat. Okay, so let's see. Have you considered a multi-partition model, just as an example, including a partition to study time evolution of concentrations beyond the blood-brain barrier? If I understand correctly, I guess what you mean is that if we have parts of the differential equations that are describes one part of the system and another one that is on the other side of the blood-brain barrier, for examples, and that is possible. We haven't studied those kind of models ourselves, but typically distributed models that are still described by ordinary differential equations with some transfer terms and so on. That is very well implementable. Okay, so is it possible to get a copy of your package? Yes, of course. It's freely available, and it's only to go to the web page, the last link in this presentation that was put on the last slide, and drop us an email, and we will provide this. Okay, and then I wish there was an even simple LME, linear mixed effects model built into Mathematica. Yes, I'm not sure how much the focus has been over the years on that. I mean, it was quite a big effort when all the generalized linear models and nonlinear models, when that was put into the Mathematica or built-in stuff. But since then, I think it has not really been in the focus. But also linear mixed effects models would, of course, be very nice. Our main aim with this package from the beginning was actually to develop or improve the algorithms. It was not from the beginning the aim to develop this Mathematica package. We used it in-house, so to say, because we could mix symbolics and numerics so nicely. So that was like that. Okay, let's see here if I had. Are there specific functionalities based on Wolfram Mathematica that offer advantages uses compared to other LLM? Yeah, that's a very good question. I would say that, okay, when it comes to the numerical implementation, this is one. I mean, we have this improved folk methods, as it's called. That has also, since we published it, it has also been picked up by the leading vendors of industrial software, like NonMem picked that up very early on when our paper came out, because it was shown that it could speed up things quite dramatically as such. So I think that the main thing in Mathematica is I mean, it's for those that like notebooks and Mathematica, the ecosystem, to have all in one system from visualizations and statistics and so on. I think it's very nice that we now have NLME stuff accessible within Mathematica. And for us, of course, it has been a very big benefit to have in developing the algorithms to have this mixed numerical symbolics and sensitivity differential equations as such. Okay, so yeah, and the next question was also similar. What is the advantage to this package compared to NonMem? I mean, we have at this point we showed that computing gradients by solving sensitivity differential equations instead of using finite differences, that was kind of industry standard before, that improves both speed and robustness in parameter estimates. Now NonMem have included them, so to say, our method into that software, which is good, I think. But we still wanted to release this for Mathematica because we saw the benefit of people already working in Mathematica to have direct access to this. And there's of course a lot of things that has gone into NonMem and developed over the years that we by no means aim to compete with. But I think it's a nice thing to have it in Mathematica now, and at least with its standard methods. Okay, can this package perform Bayesian forecasting, including priors and so on? No, it can't. It's not wired in that way. We can still, it would be easy to put in some kind of Bayesian functionality into it by including priors. That's essentially only, for us, it would only be to add some regularizing terms in the likelihood. And then, so to say, to make Bayesian point estimates and also some spread there. Full Bayesian treatments are usually more or better done by Monte Carlo methods or particle methods and so on and so forth. And that's also an active research area of ours. So that might be something for the future for us. Okay, and partition. Let's see. It seems to have been stalled. Maybe stalled is related to the linear models and or the statistical model analysis parts in Mathematica. And yeah, partitions also more useful as the drugs are hydrophobic, fat soluble, and can be more slowly released by some tissues. Yes, for sure. That's correct. Okay. And then there were more like comments or statements, I think, about factor analysis, but not mixed effects, and that it's an area that Mathematica has been lacking. Okay, can one use global search algorithms in this package? No, it's not. Yeah. Since we have the likelihood function, it was very, very easy to include it. Our focus has not really been that in that region. Essentially, we have been working very heavily on to speeding up these algorithms, using as much structures as possible, and then of course gradients are key to that. And resorting to global search algorithms that will, so to say, bring down performance with several factors. So we have not really not done that. Although it would have been nice maybe for comparison of performance and so on and so forth. Yeah, I think we are getting close to the end of the chat room. Thank you, everybody. Also, those of you that I haven't seen for a very long time, I see. Hello, Jan, and hello, James. Very, very nice to see so many people showing up this late into the conference. And if you're interested, just get in touch. We gladly share the application. We might also set up an even faster way of sharing it than just requests by email eventually.
If there's nothing else, any other questions? Thanks for giving the presentation, Mats.
Thank you.
All right. Everybody have a good rest of the conference. Thank you everyone for joining and viewing.
Thank you.